Perfect. Whenever you're ready, Jeff.
Excellent, excellent. All right. So I wasn't sure, like all these talks, that there's this different levels of knowledge about probability and stuff. So I wasn't really sure where to go. So I'll try to make a balance to meet everybody's needs. And the, oops, see, this keeps, oh, there we go. So today we're doing dimension reduction and maximum likelihood, which are uses a lot of statistics and probabilities. So hopefully that won't be such a problem. And the dimension reduction is again about, let's get rid of this. We don't want to see that. Dimension is again about compression. So you have, we talked about this before. The one person has a message they want to send, and they want to send as few bits as possible. And here's an image that we might want to compress so we can send it with fewer bits. And here's the image after it's been encoded and decoded, and we're certainly are losing quality there. But the goal is to be fewer bits. So here, this image is 100 by 100, so it's 10,000 pixels. And even just a little image like this has 10,000 pixels, and each one has its own number. And but again, the numbers, the pixels aren't just 10,000 independent numbers. There's a connection between them. And this, in fact, this kind of image recognition was I don't know, back in the 80s or something, when they made everybody look straight ahead. So the nose was always in the middle. And so there's a pattern to it, and we can use that pattern to compress the image down into only 100 numbers. So this was reconstructed from 100 numbers. Hey, Martin, we always catch you on the way home from work. All right, so we did this kind of compression before when we were talking about machine learning, and the purpose was that if you can compress it so far, then you must be somehow extracting out the pattern. You must be finding out what are the key 100 numbers to represent this, and maybe then when you do machine learning, you can learn from these 100 numbers better. And this, I don't really know when this method came about. I've certainly known about it for a while, so I just wrote down the 80s here, but I don't really know. All right, so here we have images all like looking straight ahead, and we want to compress them from 10,000 numbers to 100 numbers, and you might, so that we can use those 100 numbers somehow. So as we've said before, you can think about this, this image here with 10,000 numbers is just a vector. It's just a list of 10,000 numbers. And so you can put a dot in a space. This is a 10,000 dimensional space, right? What color the first pixel is down. We still have this thing sitting in our, all right, what color the first pixel is our first dimension, and then how bright the second pixel is, and so forth. We can get a dot. And then if we have lots of bases, then those are lots of dots, lots of points in this high dimensional space. And the idea is that they're not randomly distributed, right? There's a pattern to them, and our goal is to find that pattern. So the way we're going to do it is we're going to try to fit the points inside of a high dimensional ellipse like this. And here's another picture of a high dimensional ellipse. And then once we've done that, then, right, an ellipse has various axes, right? This axis is the long, more important axis, and then it has smaller axes. And so what we can do is we can project all the points down onto the most significant axes, right? So here, what do we mean by that, right? I think I've shown you this image before. It's a three-dimensional image which gets projected down to 2 dimensions, and clearly you lose some information in the process. So what are we doing is kind of like shining a light down, and all these points get projected down to a lower dimension. And then what's our new numbers? Well, is we can say, where is the point located along this new axis, right? So it's a rotation of the data. And if we start with a 10,000 dimensional space and we project it down onto the most significant 100 axes like this, I mean, this is projecting 2 dimensions into 1 dimension, but you can kind of imagine projecting them from 10,000 dimensions down to 100 dimensions, and that's what our goal here is, right? Everybody kind of get that picture, right? So now the bulk of what we're going to be talking about is how to take this data and find an ellipse to put around it. And I think this is just kind of useful for understanding data in general. And hopefully it's not too easy for people. So for those of you who are not completely up in probabilities, let's have a coin and flip it 100 times. All right, so let X denote how many heads you get. And so I did this experiment, right? I flipped them 100 times and I got like 53 heads. So I put a little orange box on the 53. And then I do it again and I keep getting different numbers, right? Every time I flip 100 coins and I count how many of them are heads, and we can put little boxes to say what results I got. And we keep doing that. And when you get the same number of heads twice, then the boxes kind of stack up. So that's going. And if we keep doing this lots and lots and lots of times, then you're going to get a pattern, right? And here's the pattern that forms. And it's called the normal Gaussian distribution. And we want to scale it down so that the total area under the curve is 1. One way you can do it is to have the height of each box be 1 divided by the number, right? The area, have the area of the box be 1 over the number of times you do it, so that the total area is 1. Another way I like to think about this, a curve like this a way of representing a distribution is you throw a dart, right? See here, this woman threw a dart and it landed a random place under the curve. So each little bit of area is equally likely to get hit. And right, but you have to be under the curve. And then once you get that spot, it falls down to being the X value that you've obtained. And then you repeat that process, right? You keep throwing darts at random places in the area. And if you keep doing that, you're going to fill the whole area, right? You're going to hit every place in the area sort of equally likely. And you're going to get the same. It's basically the same distribution we had talked before, right? So what do we know about this distribution? Well, you probably all know, if you flip a coin 100 times, how many heads do you expect to get, right? You expect to get 50. Of course, you saw from our little experiment here, you didn't always get 50. 50 is not what you expect to get. It's the average. If you do it a billion times, then the average number of heads you get will be 50. And then standard deviation is a measure about the sort of the variance, or how much you deviate from that mean. And we'll talk about that number a little bit more. But right now, all you have to say is, well, we flipped the coin 100 times, n times, and the standard deviation turns out to be the square root of n, which is 10. And so you can see here, I have here a distance of 10 from 50 to 60. And we're going to break up this, right? We're going to take steps of size 10, the standard deviation. And so if you flip a coin and you get X heads, then we're going to say, well, what's C? C is how many standard deviations you are away from the mean. So here, for example, if you got 70 heads, then you are 2 standard deviations away from the mean, right? Because the mean's 50 and there's standard deviations 10. And so that's what, in this case, C would be 10, 2 standard deviations away. And then you can ask, well, what's the probability that I got 70 heads, right? And it's kind of, here it's like there are 3 little boxes divided by the number of boxes I had is the probability that we get 70 heads. It's also, if we make the area under the curve 1, then the probability is the height here. And as a formula, it's you take the number of standard deviations you're away, you square it, you divide by 2, and then you do exponentiation decay on that. So it's really, it decays exponentially fast, really quite small down here. So for example, if you plug in C equals 6 into this equation, you see the probability of you being 6 standard deviations away is really pretty small. In contrast, most scientific papers, psych studies say if they're deviating away 1 out of 20, then they say, oh, something special might have happened and it wasn't just purely random. Right, everybody kind of good with, that's just probabilities. So now let's make it a little bit more complicated. Let's flip a coin 100 times, and that will be our value. The number of heads is our value x1. And then we flip it 100 times again, and that will be our value x2. And we put a dot, little square here, being for x1 and x2. And we want to see what pattern arises there, right? So we keep doing this and we have different results, right? Each of the dots says how many heads we got the first time, how many heads we got the second time. And again, if you get the same number of times, then they kind of pile up. So it comes out 3-dimensional as a height. And so we can ask for a particular x1 and x2, what's the probability that I get x1 heads the first time and x2 heads the second time? Well, because these 2 events are independent, then one, it's the stack of, right? It's the stack of height we have here. It's the height of this thing. And because of independence, it turns out, well, it's well, what's the probability you get x1 heads the first time times what's the probability you get x2 heads the second time? And remember, we had these equations already. This was exponential and the number of standard deviations squared, and again for the second one. And when you do a multiplying here, one way to multiply is you add the exponents, for those of you who are up for that kind of math. And so this is our equation, and you might say, well, what are we going to do with that? Well, let's first try to understand this probability distribution by drawing contour lines. And remember, just like in a map, you'll draw a line, right? We're trying to find the height of this probability distribution, right? There's a hill here. Clearly, stuff in the middle is more likely than stuff further out. Right, because you're more likely to get 50 the first time and 50 the second time. So there's definitely a hill here. And we can ask, well, what is the contour lines? Is a line of where everything along this line is the same probability. And you might think that the contour lines look like this, right, where you're more likely to be in the middle. But Turns out it's not quite like this. So I hope some of you knew that this was wrong. Think about a the corner here, right? In order to get something at the corner, well, you had to be kind of completely unlucky or lucky the first time, and kind of unlucky or lucky the second time, right? So the probability you had these extreme values. Well, you might get extreme value in one of them or on both of them, but you're not likely to get an extreme value on both of them at the same time, right? So that's not what the contour lines look like. So let's go back to this equation here and see what these contour lines look like. We let C be some fixed constant. And so here, this is some fixed probability. And we're wanting what are all the values of x1 and x2 for which the probability is this fixed value. And you can see that it boils down to this equation. Actually, I probably forgot. Well, the half, oh no, I got the half on both sides, so they cancel out, right? We got this equation here is the set of all x1 and x2 that have this property. And those who are good on algebra will know that that's the equation for a circle, right? So these are our contour lines, are these circles. And here's another example, I guess, where we flip the coin 3 times, right? So they all sort of fall in this ellipse. And here's our probability distribution, this nice curve. And what do we do with these curves here? Well, here's a little square, and I ask, what's the probability that when I do an experiment, I fall right in that square, right? I have this many heads the first time and this many heads the second time I fall in that square. Well, clearly, the bigger the square, the bigger the probability I fall in it. And the height here somehow is representing the probability. So we multiply those together, right? We multiply the height of this curve times the area of the square, which is basically the volume over this little square, tells us the probability of this event, right? Everybody good? That's my thing on those probabilities. So let's do a slightly more complex experiment. Before we start, we're going to fix a value P to be some value between 0 and 1. And then what will that P be? That will be used as the probability of our coin. When we have, it'll bias our coin, so the probability it comes up heads is P instead of 50-50. And we're going to use that same coin in both of these experiments, right? We choose P once, we flip the coin 100 times, we flip the same coin 100 times, and we plot how many we get. So let's think about it. Suppose that you first flip the coin 100 times and you got that x1, the number of heads, the first coin is small. Well, it could be that it was small because you were just unlucky in your coin flips, or it could be that it's small because the P you chose, right, is small, right? You have a smaller P, then you're not likely to get as many heads. And maybe that's why you got a small, is because your P is small. And then, well, if your P is small, then that means your second value, x2, is going to be likely to be small too, right? So these are just trends that if one's small, then the other is likely to be small, right? Conversely, if you flip the coin the first time and got lots of heads, then, well, that's evidence that your P might have been chosen to be big, your probability big, which will then give you some evidence that your second time you flip the coin 100 times, you'll get a big number. And so when you plot all your, right, every time we do this experiment, we get a new P and we flip it once, and we do the 100 twice. And so if you plotted them, they would probably lie in some diagonal like that. And the reason is because the value of x1 and the value of x2 are correlated, right? When one tends to be big, the other tends to be big as well, right? Does that make sense? All right, so now we want to switch over a little bit more to machine learning and how this might relate to what we're doing. So the way we do machine learning is we collect data from the world, right? Maybe we're grabbing all those faces, or somehow we collect some various D numbers from the world that we're learning, and we're going to just, like we did before, we're going to put them on our graph here, our numbers. Why? It's because we want to understand them better, and that's where our numbers went. And we say, oh, that's cool. What can we learn? Our whole goal is to get training data and to learn something about it. So we plotted this and we want to learn something. And if you were just to eyeball that, you would say, hey, dude, it looks like a Gaussian distribution, normal distribution, and that seems good. Now, we don't know where these numbers came from, right? Maybe they were how bright our papayas were when we grabbed them, right? So what we're going to do is we're going to pretend that the way we got these numbers was by doing some experiment in which we flipped a coin 100 times and we asked how many heads there were, right? So if we just have a hypothesis, right? Our hypothesis is these numbers are distributed kind of in a normal distribution way. And if that's the case, then what do we learn? Well, our frustrated guy is going to come and say, hey, dude, if these coins, if you got these from flipping a coin, then your coin was not fair, right? Because the average is not 50, it's shifted over. The average is 60 heads out of 100, right? So what did the frustrated guy learn? He said, well, if you got this data from flipping coins, it's probably because the probability of heads in your coin was not 50-50, but was 0.65 is the probability of getting a head, right? That's what he's speculating. And why did he chose 0.6, right? You can kind of eyeball it itself and you chose 6.6, but the way he did it is he used this equation here. He said, suppose that our distribution was this normal distribution from coin flips with some parameter p that we don't know. P is the probability it comes up heads. And so then this is asking, suppose we're under the world in which the coins, which all this happened with a probability of p, for each p, we can ask, well, what's the probability that we get the data? If we chose our data according to this distribution with probability p, well, what's the probability that we got our data? And which p do we want? We want to choose the p that maximizes the probability that we got our data, right? And as you can see right here in this example, well, 60 out of 100 is probably the probability on a coin such that getting this data is very likely, right? Does that make sense? And this is called maximum likelihood modeling. And when I first started taking statistics in undergrad, I hated it because it seemed so arbitrary. But as I started to figure it out, I figured out that everything they do pretty much is using this simple concept, the idea of maximum likelihood. And so let's understand it a little bit better. And before we go into a little bit more about maximum likelihood, let's just see how it connects to machine learning. All right. So in machine learning, right, we grab a bunch of data that we want to understand the universe better. So we get data from the universe. And when we train on this data, like here we get data and we train on it. What do we obtain? We obtain the value p, this parameter, this weight of our belief about the world. And then later, if we were trying to understand the future better, well, now we would know this value P that we could use in our later understanding, right? Does that make sense? So to make it a little bit more concrete, remember here, this is a probability distribution with some parameter P, which is the probability of the coins being heads. And when you have different P's, you get different probability distributions. And so for a particular P, we can ask the probability we get our data. And what we're trying to do is find the P that maximizes this, right? Well, turns out these two equations are the same, right? I just take the probability and I take the log of it and I put a negative in front. That's not going to, that would change this value, but it won't change which P is optimizing it, right? So, but it does change from, I'm trying to find the P that maximizes this, trying to find the P that minimizes this, right? Minimizing this negative log of the probability. And you might wonder why I do that, but taking negative logs of little numbers is a reasonable thing, right? This is right, say the probability here is 1 out of 1,000,000, and you take the negative log of it, you get the number of zeros, which is 6. So that seems like a fun thing to do. Anyway, let's plug in our equation. Remember, this was the equation about the probability of getting a number. Here we have how many coin flips. We got the x1 all the way up to xd. Maybe we did it xd times, and that's sort of how far we're deviating from the mean. And but if we take this number, right, it's an ugly equation, but if we take the negative log of it, then what we're left with is just for each sample here, how far we deviated from the mean squared, right? So it's the sum of, right, and this can be considered the error, right? I got this many heads, but this is the number of heads I was expected to get, right? So this is your error, and it's the sum of error squares, right? Which is exactly what we were doing in machine learning, right? We have our training data, and we're trying to get this set of parameters so that we can minimize the sum of squared errors in our model of understanding the world, right? So I think it's kind of fun that you know, this machine learning idea is completely tied to this maximum likelihood idea, and the same equations fall out, and there you have it, right? People kind of following me here a little bit?
A little bit.
Any questions? So let's do some more of this maximum likelihood idea. And again, I put the word normal here because we're going to limit ourselves to simple distributions that are normal distributions. And I'm going to kind of repeat what we said so far because maybe you didn't quite get it. Somehow we're trying to learn about the world. And in order to learn about it, we're going to collect some training data. Here are each of this is going to be a vector, right? It's a vector of a whole bunch of numbers, and this is a vector of a whole bunch of numbers. And we collect that data from somewhere. And now we're going to try to model the world based on, this is all we know about the world. And we're going to try to model the world based on this data, all right? And what do we mean by modeling the world? Is a model is a simple explanation of the world, right? And so the way we're going to do it is we're going to name various simple probability distributions, and we're going to name a lot of different probability distributions, but they'll all be simple. And what we want to do is, of all those many probability distributions, we want to choose which one maximizes the probability of getting this data, right? Had we chosen this data according to this probability distribution, the probability of getting this data would have been higher than if we had chosen any other distribution, right? And so if you're understanding what I'm saying here, then you might say, well, I have a distribution for you. Here's the distribution. With probability 1, you get this data. And with probability 0, you get some different data, right? Well, that's a probability distribution, and it certainly maximizes the probability of getting this data. But it's not such an interesting distribution. It's not such, we want somehow a more simple class of distributions that we're going to talk about. And so we're going to define this family of simple distributions here, and they're going to be parameterized by our weights. Remember, we're always parameterizing things by weights. And so you give me a bunch of numbers W, and that will define some probability distribution. And we will use that probability distribution to generate random information like those up there, right? And since we got the word normal in the title, the distributions we're going to be considering are going to be normal. If you want to know the difference between normal and Gaussian, normal are over continuous numbers, where Gaussian's over discrete, but it's the same idea. All right, so now we have all these distributions, and our goal is to find the parameters, right? For each setting of the parameters. This is conditional probability. It's the same. Before I put the weights down here, now I'm putting the weights over here. It's about the same difference, right? We're saying, given a fixed setting of all the weights, that gives us some probability distribution. And we're going to ask, what's the probability that we get our data given these are the weights, conditioned on these weights? And we're going to try that for every setting of the weights. We're going to say, well, what's the probability of us getting our data given those weights? And which weights do we return? We return the weights that maximize this probability, right? People kind of getting this? All right, so let's be concrete here, because that sounds like a lot of math. Again, remember we had an image here represented by 10,000 pixels, so it's a point in a 10,000 dimensional space. That's a complex space. We have lots of images, so that's a lot of points in our 10,000 dimensional space, and that's our data, right? Somehow we get this data, and remember our goal was to fit an ellipse around this data, and we were asking how you do that. And we're going to use maximum likelihood. So what does that mean here, right? What it means is that we know that our face data aren't random numbers. They're not random numbers, but they're numbers that came from our observing our world, right? We took pictures of all these faces, and that's where all this data came from. But we're going to pretend that that's not where the data come from. We're going to pretend that it was randomly, all these points were randomly generated from a multi-dimensional normal distribution, just like this here. This is a normal distribution, and we're going to pretend that's where we got the data from, right? That it's not just stuff from faces, but it was randomly generated, right? Now, there are lots of normal distributions, right? Right, just like when we were talking about just the simple flipping a coin 100 times, there's, well, what's the probability that you get heads and tails, right? And then maybe I can flip, remember we looked at, I flipped the coin 100 times and then I flipped it 100 times second time, but those two numbers were dependent on each other, right? Because if X1 was big, then that's probably tells me that X2 is going to be big, right? So there are lots of different of these normal distributions. And how are we going to parameterize them? We parameterize them by defining an ellipse, right? Here's an ellipse. And what is the meaning of these ellipses? Well, you've kind of seen already, these are the contour lines, right? So all the points along one contour line are going to be points that have the same probability. And the points on the inner contour lines are going to have a higher probability, right? So if you choose a random point, we have a particular distribution defined by these ellipses, then when you choose a random point, right, here's some point, what's the probability that we get this point? Well, here I have a little ellipse under here, because this is saying, conditioned on, we're talking about these ellipses, what's the probability that I get that point right there? And I'm saying it's quite high, the probability I get that one. Why? Because it's close to the center of the, close to the smallest ellipse. On the other hand, what's the probability I get this guy? Well, it's a little further out, and so it's going to be a low probability. Everybody along this 2 circle is going to have the same low probability, and everybody on a 3 circle is going to be even a lower probability, right? And if you remember our definitions, it's basically you take kind of how many standard deviations you are out, you square it, and it's sort of exponential decay based on that number of standard deviations you're out. Everybody kind of understand what this distribution is and how it relates to these ellipses, right? Now, of course, this is ellipses only in 2 dimensions, and we have ellipses in our 10,000 dimensional space. So it's a little harder to visualize, but this is what we're going for. How are people doing? Are you guys doing okay in this material? Martin, Kathy, somebody, Ali?
Yeah, it's good, thanks.
All right. All right, so what we're going to do is we're going to have a particular ellipses, particular definition of a distribution, and then we're going to choose D data items independently, right? Each of these are chosen independently according to the same distribution, and we can ask, what's the probability that we get this data, right? And because they're independent, well, it's the probability that our first point, we got our first point, times the probability we get our second point, times the probability we get our third point, right? So we can calculate what's the probability of getting this data, right? Does that make sense? Now, let's try different ellipses, right? Here's a perfectly good ellipse. It's defining a perfectly good normal distribution, right? The guys that appear here in the middle will be high probability, and anybody that appears more on the outside is going to get a low probability. And you might ask, given this probability distribution, are you going to obtain this data, right? Well, you might get this data, right? It's certainly possible, but we're going to say the probability of getting this data given this ellipse is relatively low, right? Does that make sense? Right? So what about this ellipse, right? Given this ellipse, if we were choosing our data according to this ellipse, then the probability of getting it would be higher, right? And what about this ellipse here? Of course, I'm just eyeballing these ellipses all by myself, but I would say this ellipse is the one that maximizes the probability that we get our data, right? Does that make sense?
Yeah.
Right? We're given the data and we're saying which ellipse is going to maximize the probability we got that data, right? And that somehow explains something about the world. It's saying that this data is sort of coming to us, if it was coming from us a normal distribution, and normal distributions are pretty common in the world, right? Because they relate to coin flips. And So it's not too unreasonable to expect things are normally distributed. And if they were normally distributed, then the parameters that would define them would be this ellipse, right? Most likely this ellipse, right? It could have been this ellipse that from which we got that data, but not likely, right? Everybody kind of getting that? So if we were to repeat this again, maximum likelihood, what is it doing? It says we are given our data, right? Our starting point is that we have this data. And what we do is we find the ellipse, right? The parameters of our distribution that maximizes the probability we get this data, right? So here it's kind of written again, over all possible ellipses, which ellipse, give us the ellipse that maximizes the probability we get our data, right? Does that make sense? All right, everybody good with that?
Okay.
So now what we're gonna do, we can slow down anytime because I'm gonna run out of material anyway, just to let you know. All right, so what we're gonna do now is we're gonna go back and do lots of statistics because we love statistics, right? And this is just a warning that I'm gonna explain all these equations later, right? We can talk about expected values, we can talk about variance, we can talk about covariance, and I'm gonna explain all these values right now, all right? So remember where we're starting. We're starting with lots of faces. And we're going to form a big matrix of numbers. Each row is going to correspond to one of the faces, and each column corresponds to a particular pixel. All right, so here xi is the ith pixel, right? And we can ask, what is the brightness? What's the average brightness of the ith pixel? So we take this column, we sum them all up and divide by the number of faces. Here what we are, we're summing up the brightness of all the ith pixels. And we're saying, what's the average brightness of the pixel, right? That's how bright that pixel is. And we're gonna call that the expected value of that pixel. And as soon as you talk about expectation, then you need to have a probability distribution, right? So what's our probability distribution is we have all these faces, choose one of these faces randomly, right? Because this is all the data we want. We could say choose a face from the universe randomly, but we don't, right? This is all the data that we have. So of these data, maybe we have 60,000 faces here. I don't know how many faces we have, but choose one of them randomly and look at its ith pixel and ask, what's the expected value of that brightness of that pixel, right? Which is the same as the average overall pixels, right? Something loud's happening. Hopefully it's not a fire alarm. All right, everybody good with that? And here in the picture, you can see for all of these brightness, right? This axis here tells me how bright the first pixel is. And so what's the average value of, if you just look at the brightness of the first pixel, that's the average, right? And similarly, this is the average brightness of the second pixel. And you do that for each pixel, and that locates one point in space, right? It's the intersection of all of these lines. And what's that? That's kind of the middle of our data. And that's going to be the center of our ellipse, right? Our goal is to form an ellipse, and we start by forming its center, which is the average of all of the data, right? Does that make sense? That is my fire alarm. So hopefully everything is going to be fine.
I hope.
All right. So it's confusing to have lots and lots of faces. So let's just let's look at the situation where I have two faces, right here, 2 points, and I have only 2 dimensions. I have pixel 1 and pixel 2, and we're going to try to understand our various equations, right? So here, face 1 has the brightness of pixel 1 and the brightness of pixel 2, and you might say, why did I put such weird numbers in there? But you'll see why these weird numbers come up, right? That's our 2 pixels. And what's our first number here, right? The brightness, we want to take the average of the brightness of the first pixel. And you see the first pixel is in, right? The first pixel, here's the first pixel. And for our first image, it's the value is A plus U. And for our other picture is A minus U, right? So we have 2 pictures, one with value A plus U and A minus U, right? And you can see what's the average of these 2 values, right? If you sum them up and divide it by 2, the average would be A, right? And similarly here I have 2 brightnesses, and they are some value B plus V and minus V. So if you took the average of those, you would get B, right? So that's our average our center of our ellipse is at A, B, in that spot right there, right? All right, so now we're going to talk about variance, right? And what variance is a measure of how far you deviate from the mean, all right? So let's look at our first point. What we're going to calculate here is what xi bar is the mean, right? The mean was, remember, our A. So this value is A here. And what's x1 is the value we got, right? The value we have is A, in this case, is A plus U. So we have a brightness of A plus U, but the mean is A. So what's the difference between the value we got and the value of the mean? Well, the difference is this U, right? That distance, that's how much we deviated from the mean, is U. And that was great. Now let's look at our other point. How much is it deviating from the mean? Well, it's a distance U from the mean, but in the other direction, right? So it's deviating negative U from the mean, right? We have a deviation of U, deviation of negative U, but what we're going to do with those values is we're going to square them. So this positive U and this negative U are both going to become U squareds. And then what's the expected value of that? Well, in this case, the value is U squared in both cases. So the expected value is U squared. That's the variance, is U squared. And when we take the standard deviation, what you do is you take the variance and you square root it. So that gives us back to a standard deviation of U. And why do we do that? Well, I like to think the units are right? If we're measuring brightness here in terms of, say, meters or in terms of joules or something, then the variance is going to be meters squared. Well, standard deviation brings it back to meters. And you've already seen, we've already talked about standard deviation, right? What value do we expect to get for this pixel, right? We expect to get its mean value plus or minus some number of standard deviations. Remember, being 6 standard deviations off is very unlikely, right? So then we do the same for the second pixel, right? Here it's deviating negative V and positive V. So in both cases, we're going to square them, and we got that the variance is V, right? Everybody, some of you probably know this already, and those of you who don't know it already are falling asleep, but there you have it. So now, so that's what I said before, right? What values are we going to get? We're going to get the center point plus or minus some number of standard deviations in this direction, and some number of standard deviations in this direction. So they're all going to lie on this ellipse here. And that gives us that the long axis is u and the short axis is v. That gives us our ellipse here, right? Which is just given by our center and our standard deviations, right? All right, so now let's talk about covariance. And covariance allows for us to interdependence between the variables, right? Now we were just saying, before we were looking at each variable by itself, but now we want to say, hey, if x1 deviates from the mean, is x2 likely to deviate in the same direction or a different direction, or is that independent? All right, so let's look at these two cases here. What we have here is how much is x1 deviating from its mean? And you see in this example, x1 is deviating by positive u from its mean. And similarly, x2 is deviating positive v from its mean. So we take the product of positive u and positive v, and we get uv. And what about this point down here? Well, the first one is deviating by negative u, and the second one's deviating by negative v. So we take the product there, and you get positive uv, and again, right? Each of them, even though they're deviating in opposite directions, right? You take the product of these two negatives, and you get a positive, right? So the variance is uv. So the covariance is uv, and that's because the two are positively correlated, right? You can see when one is big, the other tends to be big, and when one is small, the other tends to be small, right? That's the covariance between these two. And similarly, here are two different points, right? And you'll note that here, this guy's deviating negative u and positive v for a negative uv. Well, this one's deviating positive u and negative v for a negative uv. And either way, you get the covariance is negative uv. And that's negative, they're negatively correlated, right? When one is big, the other is small. So we just take all of these, for every pair of variables, right? We're going to take this, take the covariance. And one thing to note here, that if we talked about this early in a different day, if the covariance between them is 0, right? The correlation between them is 0, then that means they're independent of each other. All right. So, so here's just a little aside question. Suppose you grab the random face, and we have two pixels that we like, right? We like this pixel and this pixel. And you grab a random face. Are their brightnesses likely to be correlated with each other? And I say probably, right? Because if one of them's bright, then probably the image as a whole is probably bright. And so then the other one's probably bright as well, right? So they're likely more correlated. But maybe a pixel that's within the hair is going to be more correlated with the pixel in the hair, right? Because their hair is going to be a similar color. Anyway, that's what we're talking about, correlation. And one of the mantras in statistics is just because two things are correlated doesn't mean that one's causing the other. Just needed to say that. All right, so we have lots and lots of pixels. In fact, we have 10,000 pixels. So we can form a 10,000 by 10,000, 10,000 rows, 10,000 columns matrix. And the ith, take the ith column and the ith row and the jth column, it will be the covariance between the ith variable, how bright the ith pixel is and how bright the jth pixel is, right? So that's a big matrix here. One thing you might notice is that the matrix is symmetric, meaning Mij equals Mji, because if you take the covariance of the variables this way and this way, you get the same number. And what about the diagonal of this matrix? Well, the covariance of xi with itself turns out to be just the variance. So we get the variances along the diagonal, and this gives us a matrix. Everybody good with our matrix here? Right? And the matrix helps us to define the covariances, help us define the rotations of this matrix, right? If all the other the covariances were zero because we had all independence, then the matrix, then the ellipse wouldn't be rotated like this. All right, so now our goal is to find the major and minor axes of this data of our ellipse, and that turns out to be a little hard too, right? We're given all our data, right? We calculate all the expected values of every dimension, and we form this big covariance matrix, and now we're going to look at various vectors and want to know, is this vector, is that a good axis for my ellipse or not, right? Each such arrow, we're going to say, could it be a good axis for an ellipse? And how we're going to do it is we're going to say, suppose we took all our data and we projected it onto that vector, right? Then we could ask, how spread out is the data, right? Our goal is to project our data onto some vector such that it gives us a lot of information. So we want the variance along this to be really high. And the way we do that is we take our covariance matrix, and it's a matrix, so we can multiply it by this vector, and we can multiply it by the vector transpose. And that bang gives us the variance if you're moving back and forth in this direction. And so now what do we want to find? We want to find the vector that is maximizing the variance along it, right? And that, for those of you who about eigenvectors, an eigenvector has to do with what, if you have a transformation, what's stationary in that transformation. So you take this matrix and you multiply it by some vector v, and what you get is you get the same vector back, but scaled by some constant. And this is called an eigenvector, and this is the eigen value. And so you take the first eigenvector, which is the one with the biggest eigenvalue, and that's going to be our major axis. And if you know anything about matrices, they're going to have n, if it's n-dimensional, it's going to have n eigenvectors. And then the length, this length here is going to be given by the square root of the eigenvalue, right? And we chose the one with the biggest value here. And these are the more minor ones. And another thing you might know is that if your matrix is symmetric, which it is, then all your eigenvectors are perpendicular to each other, which is a nice property of our ellipse. And so now we have our faces. We use our faces to find our ellipse. And then, right, there's our ellipse. And then we project it down onto the axes that seem most relevant. And that is what took these images and turned them into these images, which is the way that people recognized faces back in the 80s.
Jeff, can I ask you to step back a second?
Yes, please.
Okay. The going back to a couple more slides. Right here.
Mm-hmm.
In pixel 1 and pixel x1 and pixel x2,
Yep.
are those pixels in the same image, or are they the same pixel in a slew of images?
Each purple dot is a different image, right? So
Right. So are these pixels, the x1 and x2, are those the location in the image, like the x and y axis address of the pixel? I guess I'm confused because
Yes.
there's no x and y.
So the pixels are, I guess the image has a dimension here and a dimension there, and
Right.
we're going to completely ignore that.
Oh.
Right? We're going to just think of each image as being a vector of 10,000 numbers. Right?
So we just put all the rasters one after the other, so it's a long string of what would have been a rastered image is now just one long string of rasters.
Right, exactly.
Okay, so then that gives us, but then, oh, I see. So then there's an x11, and then there's an x21 for face 2, x31 for a face 3.
Yeah.
And that pixel then has all these values that you are localized in this graph. And once you do that, then you can calculate, I guess you try and find the eigenvalue for that particular pixel, or do we just do the distribution for that one particular pixel?
Oh, well, so as you said, each purple dot is a different image, right? And this purple dot has its x1 value and its x2 value. And then that should have getting all these various screens to do their various here, let's see what we can do here. So you were both, so what are we doing down? Right, so we're going to collect all this data.
Right.
But
why is it on a plane as opposed to being scalars? Because those are all should be scalar values. I'm assuming a black and white image, right?
Yeah, each one's scalar.
But then why does it have an x and y if it's just one number?
Oh, because this is the first pixel, and this is the second pixel, and this is the third pixel. It's a 10,000. There are 10,000.
10,000 dimensions, because there's a dimension for every.
Each pixel has its own dimension.
I understand. Okay.
Right.
And so then, so once you plot, so you have this 10,000 of these plots, or no. You have let's say there was 20 pictures, so there's 20 dots in a 10,000 dimension space.
Yeah. Exactly. And you know, if it's hard to visualize a 10,000 dimensional space, but I can tell you right now, 10 points would get pretty lost in them, right?
Yes. Right.
So you're going to need, in order not to get lost in this 10,000 dimensional space, you'll probably need 60,000 images.
Oh, and that leads to why we have so much training data, why so much training data is required.
Training data, exactly.
Okay.
Exactly.
Okay, I understand. So it's making sense.
Yeah, and then it's just you form this covariance matrix and you get out, right? You learn something. But yeah, a lot, right? In some ways, right? I mean, here's just a quick calculation, right? This matrix is 10,000 by 10,000, right? So that's 10,000 squared numbers that we're getting out of this data. So yeah, you're going to need a lot of, yeah, I guess each data point has 10,000 numbers. So if you had 10,000 data points, then we would have 10,000 by 10,000 numbers coming in, which is nice because we would like at least 10,000 numbers, 10,000 squared numbers in order to give us a matrix that has 10,000 squared numbers, right? If you want to have 10,000 squared meaningful numbers, you probably should be getting 10,000 squared numbers to do that for you.
So you're saying get 10,000 images.
Yeah.
Right.
Right. Which goes back to, well, I guess, yeah, it goes back to how much training data you need, and you need lots of training data.
Okay, continue. That's great. Thanks.
Any other thoughts about that? Did other people? It's good that you ask questions. And any questions about this? Because I was gonna slip on to a completely different topic. So if anybody has any thoughts, all right. So what's the
Jeff,
new topic?
wait, that picture that you showed us of these, so out of the small number of pictures, or
Right.
maybe there's 10,000 pictures, you end up with these gray scales, which are the eigenvalues. Why is there different eigenvalues for different people?
I think what they do is you take all the data and using all the data, it tells you all these eigenvectors, and then you take all the data and you project it onto these eigenvectors, which boils down to taking the matrix we have and multiplying it by it, right? You take each image, take each of these images as a vector, and you multiply it by some matrix, which isn't square. It's going to be a 10,000 by 100 matrix, which will give you 100 numbers. And then once you have those, you then have you project it back. I guess you can also think about these. You can think about these yellow dots in two ways. You can think of these yellow dots as lying on this line, right? So if there are 100 of these lines that we're projecting on it, then they're in 100-dimensional space. But you can see that they're still inside of this 10,000-dimensional space, right? When we went from here to here, well, we moved them, but they're still within a 10,000-dimensional space. And so what this is those same images, and I think they're switched around. This woman, I think is this woman. So, but this is the image as seen from a 10,000-dimensional space, right? Because this has 10,000 pixels still, right? So all we're doing is when we project this is a point with 10,000 values. We project it onto another place with 10,000 values, but it's now within the subspace of only 100 dimensions. Right? Does that make sense?
In some way, sure.
And anything else people want to talk about, or right? So a point here in 10,000 dimensions gets moved down to a point here in 10,000 dimensions. So it's now every point in this space is an image, and we're just changing it from that to this. I really had no idea whether this was going to be too hard or too easy for people. All right, let's do a little bit about Bayesian. I had a lot more slides on Bayesian, but I kept most of them out because I figured by the time we got here, we would be tired. So just a little bit on Bayesian inference. It's another whole way of doing statistics. It's suppose you have a common cold, you can calculate the probability that you have a sore throat. And so this is written as what's the probability I have a sore throat conditioned on the fact that I have a cold. And right, so similarly, you can say if I'm having a heart attack, what's the probability that I have a sore throat? And these numbers are all made up by me, so don't think they mean anything. And then we can turn it around, right? What we know is if you're a doctor, you know that your patient has a sore throat, and you want to know then what's the probability that I have a common cold, right? Conditioned on I have a sore throat, what's the probability I have a common cold versus what's the probability I have a heart attack, right? And the way we do this is let this be a square of area 1, and I'm going to throw darts randomly in the square, and if it lands in the yellow circle, then A is true, meaning I have a common cold, and the probability of A is the area of this circle. And similarly, if I land in B, then B is true. So it's the probability of landing in there is the area B. And the probability that they're both true, that A is true and B is true, right, is the probability of this intersection, is the area of the intersection. And so the way we do conditional probabilities is, all right, this is conditioned on A. Suppose I told you that when you threw a dart, you landed in A. Now, given that, what's the probability I'm also in B? So it's the probability that I'm in A and B, right? It's the area of this divided by the area of the yellow circle. So that's, people get that conditional probability? And we can turn it around. We can say, well, suppose I told you that B is true. We know that we landed in B. Now what's the probability I landed, that I'm in A? Well, it's the area of the intersection divided by the area of B. So that gives us two equations, and you rearrange them and you get Bayes' law, which tells you what's this one? This is the probability, knowing that you have a cold, the probability that you have a sore throat, and we're turning it around to, if you know you have a sore throat, what's the probability that you have a cold? And the parts that are unknown here, this is called prior information. You have to know ahead of time the probability that you have a cold and the probability that you have a sore throat. All right, and so I read a whole book here on this that was kind of interesting. If anybody wants to look at it, I made slides. Whenever in doubt, make slides. So since we're running out of energy and time, I only have 1 or 2 pages on the connection between Bayesian statistics and machine learning. All right, and we're going to do it all proof by example. All right, so suppose you have a coin and it's the probability of heads is W, but you don't know W, right? That's the world that you're trying to learn. You're trying to learn W, right? And you remember in Bayesian, you need prior information, right? In non-Bayesian statistics, you don't need a prior, but here we need a prior. So our current belief is that W is chosen according to this distribution. You can see it's most likely that the coin is more or less fair, right? That's what our belief about our coin. We have a coin, we think it's more or less fair. And then we experiment with our coin. What do? We learn, we flip it 4 times, and out of those 4 times, we get ahead once. And what does that tell us? Well, why did we get ahead once out of 4, a quarter of the time? It could have been we were just unlucky. Maybe it was a fair coin and we just happened to get ahead once because we were unlucky. Or maybe the reason we got ahead once is because the probability of heads is only a quarter, right? This is sort of evidence that the probability of the head probability is a quarter. So what we're plotting here is a funny graph, right? The horizontal axis is all the various values of W. Just like this was all various values of W, and we're plotting what's the probability that we got this W. Here we're plotting all various values of W, and we're plotting what's the probability that we got a tail, a head, a tail, and a tail, right? And you'll see when W is a quarter, right? the probability of getting this data is the highest. And if their W was really high, then the probability of getting this data would be really small, right? So this plots the probability of our data, getting our data. And then we need to know, given this new information, what is our new belief about W? And we can plug all these equations into this formula, and out comes our new distribution. This is our new belief about W. So you'll see it's basically, it's kind of the average of these two. And it shifted our belief. We used to think that that W was likely a half, right? But now we've shifted down to say, well, it's more likely less than a half because we've gained new information, right? And this kind of is like, this is kind of like machine learning, right? Because we took data, we had some interpretation about the world, we collected data, and now we have a new interpretation about the world, and we can use that new information about the world to better predict the future, right? And one last thought here. You might remember that on two different slides, or at least on one slide, first class maybe, we talked about regularization. And what is this? This is, we're trying to do machine learning in which we're trying to give me the weights that minimize the error on how well our machine does on our training data. But we also want to minimize how complex our machine is, right? So you're balancing, you're trying to find a trade-off between these two, and hopefully that will give you, right, land you in a nice place. So I just think it's kind of interesting that this measure of complexity is kind of like saying, I have prior knowledge that I want my distribution of my data to be simple. I want it to come from, I have a prior belief that I want my data to be formed from some machine that has low complexity, right? And in the Bayes rule, right, we have a prior about, our prior is that our W is simple. And it turns out that these two definitions, if you crank out the math, they completely become the same. So so if you do Bayesian statistics where you have a prior about your belief about the world, it will manifest as regularizing your data. And that's all I have to say on this topic.
Thanks, Jeff.
Any thoughts?
Thanks a lot, Jeff. That was amazing.
Was it? Oh, good. Amazing is what I'm shooting for. I hope it was at a good level. What did you think, Kathy? You probably knew a lot of this already.
But I see it from a different viewpoint when I listen to you.
Right.
Yeah, and for me, it was great. You know, trying to revive some cobwebs in the back of my head from 40 years ago.
Right, exactly.
So it was good. Thank you.
And Jeff, I might be a bit like you. When I was a student, I did my best to not learn any statistics because it all just seemed too vague to me. You know, I didn't really
Right. But then Carrie, so I did kind of, as I was taking it, started to figure out that this is what they were doing. And then when Carrie came along, she was doing statistics. And whenever she had a question, I said, well, we're just doing maximum likelihood. And she got all angry at me for understanding it better than her.
Jeff,
I think Danielle had a hand up.
Oh, yeah. Daniel?
Danielle, is
Yes.
it from before or?
No, this is new. I have a question regarding complexity.
Uh-huh.
Jeff, you had mentioned at the very beginning that people seem to somehow choose a complexity of a machine, and then they go and they start training that machine. As it gets cheaper and cheaper to do this training, is it becoming a practice that people choose maybe a big machine and a medium machine and a small machine, and then hoping that maybe they can use a small machine, but at least they apply the same training data to all three machines, and then they just sort of see which one ends up being able to best respond. Is that a normal practice now?
Oh, yeah, absolutely. Absolutely, because if your machine's too complex, then you'll overfit and you'll memorize the data and you won't generalize the data you haven't seen before. So, so even if you have just tons and tons of computing power, you want to make sure that you don't overfit.
Okay, so that's
Right.
a good practice then. Okay, thank you.
And that comes back to this regularizing. I mean, it's hard, and if you want to be doing it all at once, you want to be balancing how complex my machine is you add this regularizing function, which puts pressure to keep your weight small, which is effectively making your machine, it's tying a hand behind your machine's back so that it can't be powerful enough to memorize the answers.
Cool.
Jake, did you have a question?
No.
All right. Well, that was fun, everybody. I hope it was good. And if you have any more thoughts, you can ask me. I guess next week we're doing these generative networks, which try to learn art and produce new art.
Oh, yeah.
And then the week after, I don't have that many things to say. We're going to have a group discussion about ethics. And then it'll be Christmas.
It will.
Thanks a lot, Jeff. Again, I don't see any more questions here, and I think we have 2 more sessions again after.
Yeah. So. All right. Thanks so much, everybody. Thanks for coming.
Everybody.
I really appreciate it.
Thank you.
See you guys next week.
All right. Bye.
Good night.
Bye. I'm going to pause the recording, Jeff.
Thank you, Jeff. Thank you so much.